Thanks to the organizers for inviting me to this nice series. Yeah, so this talk will be based on a couple of joint works with Vesti Apostolov, Brent Pim, and Yuri Ustinovskiy. So the place, oh, okay. Yeah, the place I want to start is with sort of the foundational point of stringy geometry, which is this kind of generalized Einstein-Hilbert action. So if I have a smooth manifold M and a closed three form H naught, I can define this integral for a metric, a two form, and a function f as follows. So I integrate the scalar curvature minus 1/12 the square norm of H plus the square norm of the gradient of f, all integrated against this weighted volume form. And here, as always, H will be H naught plus dB. And I can define this lambda quantity where I take the infimum of script f over all unit mass measures in this sense. Okay, that's defined here. And the basic point is that critical points of this lambda functional are what are called generalized Ricci solitons. So here I will define this connection nabla to be the Levi-Civita connection associated with the metric plus,
Sorry, Jeff. Jeff,
yes.
I'm sorry. There was a question in the chat
Oh,
asking.
wait, let me make sure I can see. Oh, yeah, I can't see the chat. Oh, yeah. Why do I have the 1/12 factor? Yeah, the 1/12 is a little bit mysterious, and maybe if you've seen some definition, people have different conventions. For me, I just take the usual sort of like, I guess Hilbert-Schmidt convention, I think is what it's called for the norm. But this 1/12 is kind of important, or maybe more to the point with my conventions. The fact that this 1/12 is not the same as this 1/4 is sort of a subtle point of the theory. Um, but I guess if from a distance you can, well, I don't know, just take it to be a definition, I guess. But it does sort of play a role. Um, right. So critical points are generalized Ricci solitons. So yeah. So this connection, so which is the
There is
Levi-Civita
another
connection plus a torsion
question.
term.
There is another
And
question.
does it
Does it
work with
work
other
without
coefficients? Well, work. I mean, I think it depends on your definition of work. I mean, of course, you could write it down. I don't think it would have nearly the geometric significance that it does with the 1/12. I could say that much. Um, uh, right. Right. So the critical points are these generalized Ricci solitons. So this connection nabla I will call like a Bismuth connection uh, for some reasons. And then the equation is that this sort of Bakri-Emery type Ricci tensor associated to the connection nabla vanishes. So by definition, this Ricci nabla f is the Ricci curvature of nabla plus the nabla Hessian of f vanishes. And when you sort of work that out in terms of classical objects, this is what it looks like. So this tensor is no longer symmetric, and this is the symmetric piece, and this is the skew symmetric piece. Okay. So intuitively, these are some kind of stringy generalization of Einstein metrics. Okay, and they of course arose in math physics, as the name sort of suggests. And a sort of basic point for us is that there's a Bianchi identity around, and it turns out that such structures have constant generalized scalar curvature. And so the generalized scalar curvature associated to a connection nabla and a function f is the following. So it's the classic scalar again minus this magic 1/12 norm h squared plus this extra term involving f. And again, here you kind of notice the difference between this 1/4 and this 1/12. So like this term, for instance, is not the trace of this term. It differs by 1/6 norm h squared. And that's important. Yeah, and then of course we can observe that from this point of view, with this definition of generalized scalar curvature, then this thing is really just sort of like an Einstein-Hilbert action. So this is just kind of the natural Einstein-Hilbert action for connections with torsion, if you like, and weights, this weight function f. Okay, so why do I care about these objects? So generalized Ricci solitons sort of arise very naturally in various geometrization programs in complex geometry. So in particular, they sort of show up naturally in complex geometry beyond the Kähler setting, and can be thought of as giving a natural notion of a non-Kähler Calabi. Okay, and this sort of works especially well in the setting of generalized Kähler geometry, which we've had some talks on in this series. So I'm going to sort of briefly recall what this is, although I guess probably it's fairly well known to the audience. So the classical description of generalized Kähler is a metric, a two form, and then two classical complex structures I and J, which are both integrable. Okay, so they're both integrable. The metric G is compatible with both of them, with both of I and J, which gives us two Kähler forms, omega I and omega J. And then we have this kind of matching condition on the torsions. So as always, there's a background three form in play, and then this equation kind of links all the structures around. So H naught plus dB is some closed three form, and that should be the same as dCj omega j, and then also the same as minus dCi omega I. Okay. Now, the sort of key feature of this talk is really kind of Poisson geometry, and it sort of enters the story here. So one of the first observations ever made about these generalized Kähler structures, so it kind of went in a few stages. So Pontecorvo, Apostolov, Godeshan, Grantcharov, and then finally Hitchin showed that there's an associated Poisson structure on, well, there's a few Poisson structures associated with a generalized Kähler structure, but in particular, we have this one. So pi will be one half the commutator of I and j, and then with the index raised with the metric. So it turns out that this is a real Poisson tensor. And moreover, it has some fairly remarkable properties. So it's type 2002 with respect to both I and j. And then moreover, it's kind of holomorphic in the in the correct ways. So the I20 part is I holomorphic and the J20 part is J holomorphic. Okay. I hesitate to call it biholomorphic though. So anyways, this is what it satisfies. Okay. Of course, yeah, as is again probably quite well known to this crowd, and we've probably seen already in this series, we can describe generalized Kähler structures kind of more efficiently in terms of generalized geometry. We saw this already in Roberto's talk, so I'll go very quickly through this. So if we have a smooth manifold M, we can endow the tangent bundle T plus T star with these two key structures. So first is a neutral inner product defined as follows, and then a twisted Dorfman bracket. So twisted by the form H naught. Okay, so we have this equation for the twisted Dorfman bracket on T plus T star. And then on this background, we can define a generalized complex structure, which is an almost complex structure written boldface J for my talk on E, which is both orthogonal with respect to the neutral inner product and whose I eigenbundle is Dorfman integrable. Okay, so it's closed on the Dorfman bracket. And then the fundamental theorem of Gualtieri is to sort of reformulate generalized Kähler structures as I wrote it on the previous slide in the following language. So it's equivalent to a pair J1, J2 of generalized complex structures on this algebroid, which satisfy an algebraic condition so they commute to these two algebraic conditions. So they commute, and then moreover, there's this positivity condition here. So this tensor should be positive definite. In particular, this minus J1, J2 defines a generalized metric. Okay. And then of course there's an integrability, like all of the integrability conditions are wrapped up in the fact that just J1 and J2 are integrable generalized complex structures. Okay. All right. So we now want to kind of specialize this sort of generalized Ricci soliton condition to the world of generalized Kähler geometry. So yeah, in generalized Kähler geometry, we kind of have two natural Bismuth connections. So every Hermitian structure has a unique Hermitian connection with skew symmetric torsion that I also call the Bismuth connection. So we have two of them now, nabla I and nabla J, and they can be expressed using the torsion condition as sort of plus H and minus H. And then it's sort of just an elementary fact. It follows that one of these connections satisfies this generalized Ricci soliton condition if and only if the other one does. And in that case, we call it a generalized Kähler Ricci soliton. Okay. And then this is sort of a little bit more precisely the right notion of sort of Calabi-Yau metric for generalized Kähler geometry. So it's strictly an extension of the notion of Calabi-Yau and also an extension of the notion of a steady Kähler-Ricci soliton. Okay. Yeah, and then by this elementary observation I mentioned on the first slide, any generalized Kähler-Ricci soliton, moreover, has constant scalar curvature. In which case we'll call it, so in the Kähler world, we would call this like cscK, constant scalar curvature Kähler. Here we'll call it cscGK, so constant scalar curvature generalized Kähler. Okay. And then, yeah, so they'll satisfy this equation. So the scalar curvature of this Nabla connection will be constant. And again, it doesn't matter. I suppose I should have decorated it with either I or J, but it doesn't matter. It's the same quantity for both connections. All right, so the kind of broad motivating question for what I'm going to talk about is to try to give some kind of extension of this famous kind of Calabi program in Kähler geometry. So I want to try to find the correct conditions on a generalized Kähler manifold, or sort of more precisely a generalized Kähler class, which I have to say what that even means, which can guarantee for us the existence of either a generalized Kähler-Ricci soliton or a constant scalar curvature generalized Kähler metric. And of course, in the world of Kähler geometry, this is a very hard problem that's sort of in the fullest generality still open to this day. But okay, yeah. Sort of to start unpacking this, well, I'm first going to kind of pare the question down to a sort of smaller class of generalized Kähler structures, which are, I guess, in a sense, philosophically closest in spirit to classical Kähler structures, which are the symplectic type generalized Kähler. So I'm not going to even really define exactly. I mean, there's a definition in the language of generalized geometry of what this means, but I'm just going to say in a very classic way what these things are and sort of describe them in a slightly different way. So if I have a symplectic form F which tames an integrable complex structure J, then I can obtain like the taming condition allows me to sort of write down this formula. So I can look at F times J minus F times J, and it will be a Riemannian metric plus some two form B. And then this data together will define another almost complex structure. So I can define an endomorphism I by just conjugating J in the right way by F. And then this sort of trivially squares to -1. And then it turns out if this I is also integrable, then the data GBIJ is generalized Kähler as defined before in the classic setting. So this is kind of a very efficient way of constructing generalized Kähler structures. And so what we're going to try to do is construct these symplectic type generalized Kähler on a fixed holomorphic Poisson background. And so what this means is sort of in terms of the way I described things before, we're going to fix J, and we're going to fix what we expect to be the J20 part of the associated Poisson tensor. So that's what we're calling the holomorphic Poisson kind of background. We're going to kind of think of that as fixed once and for all, and then try to construct a generalized Kähler structure which is compatible with all of that. Okay. And it turns out, I guess this is an observation, I think it's originally due to Marco. The equation you have to solve, so if you think of J and sigma as fixed, then this is the equation you need to solve for a symplectic form F. And if you can do this, then we've solved all of the equations above. So this equation sort of thought of in this context purely as an equation for F on a fixed holomorphic Poisson background sort of is the generalized Kähler condition. And you see right off the bat that, well, it's nonlinear. And this is sort of a key feature of generalized Kähler geometry is that kind of the natural classes of structures that we have are not linear, whereas of course like a Kähler class is a like an open cone in some linear space, right? You just have linear interpolation of any two Kähler metrics, say in a Kähler class, or just any two Kähler metrics, period. Whereas here, there's no sort of obvious way to take some kind of linear interpolation between two such solutions to this. All right, but yeah, so if you can solve this equation, then indeed the structure is generalized Kähler, and the Hitchin-Poisson tensor pi will be the real part of sigma, and then we've prescribed the data as I described. Okay. All right, so it turns out that there is a natural way of, well, there's a few ways of kind of naturally constructing such solutions to this equation. And well, there's kind of two key ones for us. And so the first one comes out of sort of, it kind of has a long history in generalized Kähler geometry, but it sort of came out of works of Hitchin and then Goto and then also Gualtieri, what they call sort of Hamiltonian deformation by a Poisson tensor. So let me just write down a particular theorem, which I guess this should be, as stated, this should be credited to Marco. So here's the statement. So I fix, again, a holomorphic Poisson manifold, which moreover admits a Kähler metric omega. So it's really a Kähler manifold. Then for sufficiently small t, I can construct like a little family of generalized Kähler structures, J1, J2, such that the classic data has the following properties. So the complex structure J is actually just fixed. But I'm actually going to deform the Poisson tensor. So the JT part of pi will be T sigma. And then the complex structure I, well, it's a deformation of J whose Kodaira-Spencer class is sigma omega. Okay. So what this is doing, so this is, I guess, sort of different from what I said on the previous slide. So we're not fixing the holomorphic Poisson geometry. We're kind of fixing the holomorphic geometry, I guess, of J, if you like. But then we're kind of turning on the Poisson tensor. So we're saying that for sort of small Poisson tensors close to zero, so this T is quite small, right? You can kind of you can turn on this Poisson geometry. And then, of course, I will be well, it's sort of close to J. So of course we're kind of taking the generalized Kähler structure, which is just determined by like omega JJ. That's a Kähler structure, which is trivially a generalized Kähler structure, and then we're deforming in this fashion. In most of the cases, we'll consider this class as zero. And so IT is actually biholomorphic to J, but it will be strictly different as a tensor. Okay. So we're kind of taking this Kähler manifold and we're simultaneously turning on the Poisson geometry and then sort of deforming J, or well, deforming the second complex structure, which starts out also as J to be I sub T. And this is how it deforms. Okay. So this nice theorem sort of allows us to kind of leave the Kähler world into the strictly generalized Kähler world on certain Kähler backgrounds. Okay. But there's there's kind of another way. So I kind of like to think of this deformation in the previous slide as kind of changing the generalized Kähler class. So really, a generalized Kähler class exists on a fixed holomorphic Poisson background. And so in the last deformation, we were kind of changing the Poisson tensor, turning it on. And here, so that's kind of like changing the generalized Kähler class. But now I'm going to kind of fix the generalized Kähler class, but still show that there's a large class of deformations. Okay. So as I said, yeah, this class of symplectic type generalized Kähler structures is nonlinear, but nonetheless, there's a natural deformation class that you can write down using a pi Hamiltonian diffeomorphisms. So here we go. So yeah, so if I have phi t, a one-parameter family of functions, I'll call a canonical deformation a one-parameter family GT, BT, IT, and J like this. So again, the J is fixed. And I deform as follows. So DTF is capturing both the time derivative of G and B, and it's DDC I sub T of phi. And then I is evolving by the following endomorphism. So by pi DDC IT phi T. Now, in a sense, morally, this is kind of like, so in the case I have I equals J and pi is zero. This just, of course, is moving in the Kähler class, right? This is just the standard thing of just deforming by a Kähler potential. But you can see by the way these things are coupled, I really have to use like DDC and then I is of course like flowing. This is just it's just something else. Okay, so and kind of more to the point, thinking in terms of these deformations, you really sort of only have like potential theory on an infinitesimal level. And this is, of course, this is all just tied in with the fact that this space is nonlinear. This is just like what I was saying, that you don't really have any natural linear interpolation of any two generalized scalar structures, but you at least have kind of a scalar, a clean scalar deformation theory coming from these canonical deformations. All right, so with this in mind, I'll write down the definition of a generalized Kähler class. So generalized Kähler depends on a Poisson tensor pi, a real Poisson tensor pi, and a de Rham class alpha. And so I'll just think of it as two forms F, which are closed, belong to the class, and then satisfy this condition of Marcos that we saw before. And the key point is that so you can use the Hodge theory in generalized Kähler geometry to show that any path in this space GK pi alpha arises from a canonical deformation. So somehow these are naturally capturing sort of, if you like, connected components of this space. Okay, so these canonical deformations are sort of they're generic in at least in terms of deformations of this within this GK pi alpha. But it turns out it's actually a really interesting question that comes out of this theory that I really don't know the answer to, and it's kind of looking like the answer might be no. It's not clear if this set is connected, um, which is kind of a strange thing coming from Kähler geometry, but it may indeed end up being the case that yeah that this will have multiple connected components.
Jeff, can I have ask
Yeah.
something? So
Hmm.
the formula for GK means that the 2 0 plus 0 2 part of F is controlled by the
Yeah,
Poisson tensor. Okay.
exactly. Yeah. Like if pi is 0, this is just saying that f is 1, 1. Yeah,
Okay.
exactly.
Thanks.
Exactly. Yeah, any others? Um, okay. So yeah, so well, we kind of have the notion now of some interesting generalized Kähler classes provided by Gualtieri's theorem, and we kind of know a bit what they are. But of course, much of the story of kind of Calabi's of the Calabi question is wrapped up in the moment map formulation of the constant scalar curvature Kähler condition. And so it turns out that there's an analog of that story in the generalized Kähler world. And this is due originally to Goto. So if I have Fj, a symplectic type generalized Kähler structure, so it turns out we can define a formal Kähler structure on this space GK pi alpha by the following formulas. So here I've chosen to write it in the generalized language, well, because it's kind of you're just writing down the obvious kind of natural symmetric space metric on this space in terms of the generalized geometry. So the symplectic form acting on variations of J1 and J2, again, this is just the kind of obvious symplectic form that we would write down on the corresponding Lie group. And then similarly, the metric acting on these two is again just this kind of most obvious biinvariant metric. And I always feel like this is kind of a triumph of the generalized point of view, because from the point of view of generalized geometry, this is the most obvious thing to write down, and it turns out to be really natural and give all kinds of nice consequences. Whereas if all you kind of knew was the bi-Hermitian formulation, you would struggle to guess these formulas. In fact, we write them down in a paper that I'll sort of talk about soon. We kind of have reason to kind of grind these out a little bit in terms of the classic data, and it's sort of an unfathomable formula. Um, so yeah, it's a really nice thing that the generalized world gives you. So in any case, we do have a formal Kähler structure on this Kähler class. And then there's of course a natural group action. This is of course the start of the story of the Fujiki-Donaldson moment map. So this group Ham F will kind of act on the space of symplectic type generalized Kähler structures. And of course, we'll, as usual, identify its Lie algebra with smooth functions with zero integral as follows. So minus f inverse d phi sort of defines a tangent vector to the space of Hamiltonians. And yeah, and this group will act on GK pi alpha in the obvious way. So you just let it pull back the complex structure J. And and yeah, and you'll produce a new generalized Kähler structure. And then the theorem of Goto is that this action is actually Hamiltonian. And what that means is there exists a well-defined function that we'll call gscal fj, such that this pairing, sort of defined as follows, is a moment map for this action. And yeah, this is generalizing the classic Fujiki-Donaldson observation that the scalar curvature in Kähler geometry is the moment map for the action of the Hamiltonian group on a Kähler class. Okay, so this is a very nice observation of Goto. But it's actually kind of an interesting side note to the story. So it's a very beautiful theorem. It also leaves a lot of interesting questions open. The first of which is that so he defines his quantity. In a sense, he sort of shows that the moment map exists, and then just calls that the scalar curvature. And more to the point, the formula is written down purely in terms of the kind of underlying spinors defining the generalized Kähler structure. So a priori, we didn't really even know what it was, what the scalar curvature was, in the sense of sort of some concrete formula. But we rectified that. So in joint work with Apostolov and Ustinovskiy in 2023, we showed so Goto's definition also depends on a choice of measure. So it needs a choice of measure. So if we have a generalized Kähler structure and then we think of the measure parameterized as follows, so the measure can define a weight function f by this formula, then Goto's scalar curvature, depending on the generalized Kähler data and the measure mu, is exactly this guy we saw from before. Okay, so it's exactly the thing showing up in the string action. So this sort of at least closes the circle of ideas that at least we're talking about the same thing, or that this Goto moment map is capturing this sort of notion of constant scalar curvature that we want. Okay.
The group it's only Hamiltonian simplex morphism for F. There is no other. There is no B field part.
Right. Yeah. Yeah.
And the
Right.
formula. Can you go back to the formula? It's just the generalized scalar. Okay.
Or sorry, which formula?
Yeah. The moment. Yeah. It's fine. Okay.
Yeah, it's a little bit mysterious. I mean, in a sense, there is an explicit formula that he gives, but it's purely in terms of these underlying spinors. And even then, it's sort of like a choice of local spinor, and you have to prove it's independent. And I mean, the theorem I mentioned identifying it is, well, it's maybe not particularly hard, but we have to do this trick of like approximating the structure by non-degenerate generalized Kähler. Where there the connection between the kind of classic data and the spinorial formulation is very explicit, and then you can just do the calculation.
Okay.
Yeah.
And F corresponds to one of the two GCS, right?
Sorry, can you repeat?
F corresponds to one of the two generalized complex structures. The capital F, or it's a mix of.
I don't. Oh, right. I no, I don't think quite. Or I mean, maybe conjugated by B. Yeah, actually, I don't remember offhand. But yeah, I mean, I think up to conjugation by B. Yeah, I think so. I
Okay,
think
thanks.
so. Yeah. Yeah, and then just as a remark, this whole talk is kind of in the symplectic type setting, but all this kind of general moment map discussion is totally general. It works for any generalized Kähler. Okay. So the next piece of the puzzle in the Fujiki-Donaldson framework is kind of identifying the Kähler class inside this complexified orbit of the group of Hamiltonians. So it turns out, so now I have to kind of to get where I want to go, kind of rapidly go through some further structure theory associated to this. So it turns out that so using Moser's lemma, you can show that curves in GK pi alpha do map to this complexified orbit. So the same as what happens in the Kähler world. And then moreover, you can extend the moment map naturally to this complexified orbit, which is usually the Mabuchi energy. And so what it gives here, at least, is the so-called Mabuchi one form. So for a function phi, you can define a kind of canonical tangent vector on the space GK pi alpha that we call x phi. And then this one form acting on x phi is exactly this sort of integral of phi against the generalized scalar curvature. So it turns out that again, this is all sort of sort of formal moment map theory. This one form is closed, but again, this kind of issue of do I really understand the topology of the generalized Kähler class kind of rears its head, and so you can at least kind of locally write down a Mabuchi energy, but for instance, you don't know if that space that I wrote down is like simply connected, for instance, right? So it's not clear that you can necessarily get a global Mabuchi energy. But that's not so important. The one form is kind of enough for us. Furthermore, yeah, uh, get we can define a metric on GK pi alpha like at the level of potential functions as follows. So again, potential functions are thought of as tangent vectors to this space in the way I described before, and then their inner product at the point F is just the natural L2 inner product with volume form F. So this is like the analog of the Mabuchi geometry. And it turns out, yeah, that again, all of these formal properties that we know from the Kähler world kind of carry over. So this local Mabuchi is geodesically convex. So this metric defines some geodesic equation, and then yeah, then this Mabuchi energy will be convex. Okay, along geodesics. And then, in particular, there's a key subclass of geodesics that arise. So if I have an F non-Hamiltonian J holomorphic vector field, so expressed here as follows. So Y is a Hamiltonian vector field like this, but if I impose that it's also J holomorphic, well, then the flow of this vector field defines a geodesic. Okay, in this space. So the pullback, the one parameter family of pullbacks will define a geodesic in this space. And this is another feature of the Kähler setting. Okay. So these ideas together kind of lead us to this last sort of key definition, which is the Lie algebra of reduced automorphisms. So here again, these are kind of formally. So this is the definition. So the Lie algebra of reduced Poisson automorphisms, I'll call vector fields like this, which again, you can see formally it's like the complexified orbit of the Hamiltonian group, which moreover are holomorphic. And then this algebra can be integrated to yield what we call the Lie group of reduced Poisson automorphism. So I'm decorating this further with sigma because you can show in context that these also will preserve sigma. Okay, so they're also Poisson automorphisms. And then a theorem that we showed a few years ago is that if you do have a constant scalar curvature generalized Kähler, then we have this nice statement. So I can define this group K naught, which is the reduced automorphisms inside the Hamiltonian group. And then I take the connecting component of the identity. And then you can show that this is a maximal compact connected subgroup of this group of automorphisms. And in particular, this group is actually reductive. Okay, so this group of reduced automorphisms is the complexification of this group K naught. Okay, so this is like the Calabi, Lichnerowitz, Matsushima obstruction.
Jeff, is there a clean formula for the geodesics?
Yeah, well, yes. I mean, at the level of like the two form F, yes. The problem, as ever, is that you don't really truly have scalar potentials. So there isn't really a global way to write down the equation in terms of a scalar potential. But at the level of the two forms, yes. And of course, it's sort of formally identical to what happens in the Kähler world, where the kind of main observation that underlies a lot of the regularity theory is that you take the space-time track of the geodesic, and then you take a product with a sort of trivial S1 factor, and then there's like a formal Kähler form you can write down on that space, and then that thing satisfies a degenerate Moncham pair. So it's
Okay.
like a boundary value degenerate Moncham pair, and the same thing is true here. So there's like you can take formally you can take a one parameter family of symplectic forms that satisfies the geodesic equation, and then do this same trick of taking a product with a circle. And then there's a natural symplectic form you can write down on that, which whose top exterior power vanishes. So it's like
Okay.
it's sort of like a degenerate Moncham pair for this, yeah, for this kind of space-time F. Yeah.
Okay, thank you.
Mhm. Yeah. So now we can say I can kind of go back now to this kind of Calabi program and state it a little bit more precisely. Okay. Or oh, sorry, before that, let me just state one corollary. So a corollary of the previous discussion is that if I have two constant scalar curvature generalized Kähler structures connected by a smooth geodesic F, now that's a big ask, and even in the Kähler world, that's not really always possible. Uh, but um, but if they are connected by a smooth geodesic, then in particular there exists some vector in the Lie algebra of reduced automorphisms, such that this geodesic is just pulled back by this symmetry. Okay, and in particular it's saying that you have uniqueness up to the action of this group. Okay, so it's like a formal uniqueness result. Okay, up to the action of this group. And right, so now we can kind of say a little bit more precisely, maybe what is this generalized Kähler-Calabi-Yau or generalized Kähler-Calabi program? Okay, so I want to express the obstructions to the existence of a cscGK structure in maybe some connected component of this GK pi alpha in the form of some complex algebraic notion of stability, which presumably has to take into account the complex structure, the Durham class that F lies in, and the Poisson geometry. And when they exist, show that they are unique up to the action of the connected component of the identity of this group of Poisson automorphisms. Okay, so a little bit more precisely, this is maybe what we're trying to do. And just as a remark, in the toric setting, in the toric invariant setting, basically all of this can be made to work completely rigorously. And this was done in joint work with Apostolov and Ustinovskiy. And then it turns out that in the end, just like just like in a toric Kähler setting, we know that existence is exactly determined by this uniform K-stability notion for the underlying Delson polytope. And it's sort of exactly the same here. So even though the Poisson geometry is turned
GP,
on,
there is a
I
question in
see,
the
I
chat.
see. I'm just going to finish and then yeah. So even though there is some Poisson geometry turned on, like a lot of the structure is the same as in the Kähler case. So there's like in particular the geodesics are sort of literally the same. That they're literally exactly the same as geodesics that you find in the Kähler world, even though the underlying structure is of course not um, uh, Kähler. And the notion of stability is exactly the same as the one in the Kähler world. It's the so-called uniform case stability for the underlying Delson polytope. So yeah, I see this question. Is the metric bi-invariant? Which metric? Which metric do you mean? No, I mean these are just in this correlate, these are just some cscGK. I mean, it can be, yeah, I don't know. It's just some constant scalar curvature metric. Okay. But so yeah, so what the toric case is telling us, which of course we kind of already knew from the Kähler story, is that there should be some notion of stability underlying this existence problem. Okay, but then how do we move beyond the toric setting? And by the way, how long do I have? Can someone say?
You have an hour, and you still have 30 minutes, I think.
30 minutes. Oh, okay.
Oh,
Okay.
maybe 20. 20.
Okay. Anyways,
20.
yeah, we'll see. Yeah. So I need to recall some definitions, which well, it's sort of a lot to write down, but let's just sort of recall some of these fundamental definitions. So a Kähler test configuration associated to a compact Kähler manifold X alpha. So alpha is always denoting the class, the Kähler class. So I have script X, script A. Is the following data. So it's a flat morphism from X to P1, a C star action rho on X, which covers the standard C star action on P1. Call that rho naught. A C star equivariant biholomorphism from X minus the central fiber to this space, to X cross P1 minus 0 with the action rho naught. And then, yeah, this Kähler class A is, so it's a 1-1 class on X, which sort of after this equivariant identification on each fiber is identified with alpha. So on each fiber, it's identified with alpha. Yeah, and we're going to sort of upgrade this definition. So we have this notion of a Kähler test configuration. We're going to upgrade it to what we call like a Poisson test configuration. So if I have a holomorphic Poisson tensor downstairs on X, then the test configuration is sigma Poisson. If further there exists an invariant holomorphic Poisson tensor that we'll call capital sigma on X, such that this identification B naught that we had from before just becomes an identification of holomorphic Poisson manifolds. Okay. It's just kind of the most obvious way to sort of include the notion of a holomorphic Poisson tensor in the notion of a test configuration. And then, yeah, so with this notion of test configuration, we can define notions of stability. Okay, so in particular, this relative K-stability. So if C is a subset of of Kähler test configurations of this space, and then P is the subset of product test configurations, then we have these standard notions. So we have the notion of a K semi-stability with respect to C. So if for every test configuration in C, the Donaldson-Futaki invariant is non-negative, and then polystability is what happens if you can also characterize the equality case. So if the invariant vanishes, if and only if your product. Maybe I see the question in the chat. Maybe I answer that at the end if it's okay. I would rather not go back. Maybe if that's okay, I'll answer it at the end. But so we want to kind of now define some notion of kind of Poisson stability, but I want to be, I kind of have to give a, well, the notion that the right notion that we want of product test configuration is slightly non-obvious. It's mostly the obvious thing you would do with one important kind of note at the end. So this data from before we'll call sigma Poisson product test configuration. If first of all it's a product Kähler test configuration, so that kind of stands to reason. So it's canonically identified just with so if here I'm removing the infinity fiber, and then it's just canonically identified with X cross C. And moreover, this sigma is kind of equivariant in the right way. So on each fiber xz, it's just defined by the right pullback of this fixed tensor sigma. So this is just sort of an invariant, like an equivariance property for the Poisson tensor upstairs. But then the key point for us is that so the limit as you approach the central fiber of this pullback. So this is just really the Poisson tensor over the fiber at Z should be some sigma naught, which lies in the orbit of the reduced automorphism group acting on sigma. So basically, we're by hands putting in like a Hilbert-Mumford stability criterion for what we mean by product Poisson test configurations. Okay. So all of this is just kind of following your nose definition, basically, of like what it ought to mean, but then we're forcing that it actually kind of satisfy this kind of Hilbert-Mumford type stability criteria. And yeah, but with this notion, we can then define in the kind of usual way what we mean by Poisson K semi-stability and polystability. So here, yeah, I fixed a holomorphic like Poisson Kähler manifold, actually. And right, so we say that it's K semi or polystable with respect to C, which is the set of sigma Poisson Kähler test configurations, and then P will be these product test configurations as I defined on the previous slide. Okay, so this is what we'll mean by semi or polystability of this data. Okay, and again, for emphasis, I just want to emphasize that here I really am just talking about the stability notion over a Kähler manifold. So I'm kind of going all the way back to the beginning of the talk, and we're going to kind of do these Gualtieri deformations away from a Kähler structure to start the story. Okay, but it's important just to mention before getting going, like the effect that this definition has. So of these Poisson product test configurations. So if I have a Poisson tensor sigma that is not polystable in Hilbert-Mumford sense, in other words, there exists some C star action rho such that you have this property that the limit as you approach zero of the pullback is some tensor sigma naught, which does not lie in the orbit of the reduced automorphism group. So if this condition fails, then the point is there exist product Kähler test configurations which are not Poisson product in the way that we describe, basically by definition. Okay. So, yeah. All right. So now finally we can state maybe a very precise conjecture that's sort of in the realm of this Calabi program, at least in this very special case. Although here I'm calling it like infinitesimal GKYTD. Maybe I explain that or why I call it that. So yeah, so I'm fixing a compact Kähler holomorphic Poisson manifold. Then I say the following are equivalent. Oh, well, the conjecture asks that the following are equivalent. There exists some epsilon depending on the data such that for sufficiently small epsilon, this manifold, so where I turn on the Poisson geometry just a little bit, this lambda sigma, admits a cscGK structure, that should just be equivalent to this Poisson K polystability of this data. Okay. So it's sort of, well, this condition in particular will imply like the classic K polystability. So we expect sort of the sigma equals zero is just the Kähler question. So then it's just sort of a YTD. We expect there to be a CSC or maybe extremal Kähler structure. And here we're kind of expanding that in a kind of small ball of small Poisson tensors around the Kähler structure. Okay. So that's maybe the explanation of this word infinitesimal. Right. And then so here finally is the main theorem of the talk. So right. So if I have X, a KX inverse, a K polystable smooth Fano variety, sigma a holomorphic Poisson structure on X, then this data, and this is just the canonical Kähler class, this is Poisson K polystable if and only if sigma is polystable in the Hilbert-Mumford sense for the action of the automorphism group of X. And in this case, there exists, the conjecture holds. So there exists an epsilon as above, such that we do have a symplectic, in this case, cscGK structure, F lambda in this class, whose associated Poisson tensor is lambda sigma. So it's sort of exactly what I was saying. So when you have this algebraic condition of, or well, thought of like this, we kind of have this very special Kähler manifold, so a Kähler-Einstein in particular, so K polystable smooth Fano variety. And then we want to ask, so we always have these kind of Gualtieri deformations, which produce generalized Kähler structures kind of for small values of sigma. And we basically want to ask which of those admit CScGK. And then the point is the answer is governed purely by this kind of stability criteria, purely by this algebraic criteria. Okay. Okay. So yeah, so this has some corollaries. So in particular, we can give some kind of very precise answers in some special cases. So on P2, the following are equivalent. So sigma, a holomorphic Poisson tensor, is polystable for the action of PGL3C. Again, this is the stability criterion. And so it turns out this can be characterized algebraically by the following condition. So the anti-canonical divisor has some explicit description. It's either a smooth cubic or 3 lines in general position. That's the same as this data being Poisson K polystable the way I described it before. And then the real point is all of that is just equivalent to the existence of these cscGK structures in these classes. Okay. And then kind of more generally on Del Pezzo surfaces, but polystable Del Pezzo surfaces, we kind of get the same kind of result. So here I've only stated it as like an existence, not a complete equivalence. There's a few things missing to get a complete equivalence, but the point is at least we have an existence statement. So we have these symplectic type cscGK in the following settings. So X is P2 and sigma is as described before. In the case of, excuse me, P1 cross P1, we have, again, like an explicit description of the relevant Poisson tensors. It's either toric or the anti-canonical divisor is smooth or twice the diagonal. In the case of the blow up of 3 points, sigma again is either toric or has a smooth anti-canonical divisor. And in every other case, sigma can be anything. They're all stable, as it turns out. Okay, so we have a very complete description of when you can do this deformation. And then, yeah, maybe I just spend a few minutes to describe the proof of what goes into this sort of infinitesimal YTD theorem. So the first thing we have to do, of course, part of the long-term goal of this is we maybe hope it may be possible to say something about the moduli of Poisson tensors on at least, for instance, Fano Kähler manifolds using this theorem. But of course, that space in general is not smooth. So we can't really expect to do some analysis directly on the space of Poisson tensors. So we kind of just have to release the Poisson condition and just look at bivectors, like holomorphic bivectors in the right space. So again, like it's really the Poisson condition that's giving it all this kind of subtle singular structure. So we just remove the Poisson condition and then we prove a version of this Gualtieri deformation for non-integrable Poisson bivectors. And what I mean is that we can kind of solve that nonlinear equation, this kind of fj plus j star f equals this nonlinear term. We solve that where we just don't actually impose that sigma is actually Poisson. Okay, but it's a power series argument and we can do it. So then now the point is we're also kind of, once we do this, we're kind of working with like almost generalized Kähler structures. So we're kind of releasing the integrability conditions, and I'll call that AGK. And again, the whole story of Poisson geometry on or not is taking place like in a fixed de Rham class. And so we can take these structures that we produce and apply Moser's lemma and just think of everything as happening with respect to a fixed symplectic form. And again, this is a kind of a standard trick in the Kähler world. Next, so, the part of the difficulty of the problem is that there's, a finite dimensional group of automorphisms. This is always, even of like the underlying Kähler-Einstein structure. And this always causes some problems with kind of implicit function theorem type arguments. But the implicit function theorem can at least usually succeed in showing that you can kind of kill off the piece of the generalized scalar curvature, which is orthogonal to this space of automorphisms. And this is like a Lebrun-Simonka type argument. So yeah, so by an implicit function theorem argument, we can at least kind of solve the constant scalar curvature problem up to a piece that lies in this finite dimensional space of killing potentials. So basically what happens then is we now kind of have what we've now kind of produced like a slice map, and we're kind of pulling the scalar curvature moment map framework, like this Goto moment map framework, back to like a finite dimensional problem now. So essentially now we just have a map on this space of Poisson tensors into some finite dimensional space, which is a moment map. And so we have a finite dimensional GIT problem on this space of Poisson bivectors. And a key point for us is that this slice map with all the relevant complex structures in play, it's holomorphic like at the origin, at the zero structure, but not in general. But this is enough, and in fact, to prove this is actually where the restriction to Kähler-Einstein comes in. It's kind of a delicate calculation to compute the differential of this map. And this is why we restrict to the Kähler-Einstein setting. We need that to prove this is holomorphic. But the point is, it's sort of holomorphic at one point, but not in general. And so, in the usual kind of like finite dimensional Kempf-Ness theory, you would have like a Kähler structure that you're working with. But here we don't. We kind of have to use a symplectic form which only tames the relevant complex structure. Okay, so we have, yeah. And so the point is, we kind of have to adopt the standard finite dimensional Kempf-Ness theory, these GIT arguments, to this setting of a taming complex structure. Okay, but indeed you can make it work. And again, the argument is basically the same. You use the moment flow, you use the flow of the moment map, and the kind of key estimate, as always, is this kind of Loyasevich estimate that we'll always have in the finite dimensional setting. And you can get a critical point. And by the assumed K polystability, we know that this critical point that we hit indeed lies in the complexified orbit of sigma. So here's where the stability condition kind of plays a role. Yeah. And then there's, again, another kind of trick using the obstruction theory. You can show that again, in general, I kind of, for the purposes of this talk, I kind of removed the notion of extremal metric, but it's not that important for what I'm saying, but it does kind of raise its head here, where really all we get is a critical point from the moment map, which generally would be an extremal structure, but you can, again, use structure results from the like obstruction theory to show that this extremal vector field is actually constant. And so because there is a constant scalar curvature metric kind of in this class, the critical point, in fact, is just a zero. Okay, so it's not actually extremal, it's constant scalar curvature. And then just as a last remark, all of these constructions, we were kind of forced to work in a finite, some fixed large regularity space. It's not really a deep regularity issue, but it's in a fixed regularity space. And so we have to show an elliptic bootstrapping result for symplectic type cscGK structures, which then finally shows that the thing is smooth. So yeah, thanks for your attention.
Great. Thank you for your talk. So are there any questions? Maybe you should start with the one from the chat.
Yeah. I can start with the one in the chat. There's a general result that a nice enough distance function on a Lie group is biinvariant. Well, okay. I mean, I think so. Yeah, what you're saying, I think the answer is yes. I think maybe I misunderstood the question. You said like the metric, these CSC metrics, of course, have nothing to do with that. But yeah, but the formal metric, like this formal metric, yes, is formally like a biinvariant metric on an infinite dimensional Lie group. Yeah, exactly. Yeah. Which kind of, yeah, in a kind of morally predicts some of these nice properties that come out. Yeah. But they all have to be proved directly. Yeah, Mario. I see.
Yeah, related to my question before. So can the moment map picture be extended when you consider like the automorphisms in the, in the subgroup of automorphisms of the current algebra which fix one of the two generalized complex structures? And I'm thinking that the capital F is the...
Yes, in fact, that is so yeah, I pretty much the whole talk was in this symplectic type case where it's a little bit easier to describe, but what you say is exactly the point for making it work in general. Yeah.
Okay.
In the generalized Kähler case, that's the way you have to think. Yeah, you
Okay.
fix one of the generalized complex structure. Yeah, exactly what you say.
Okay.
Yeah.
Okay. Are there any other questions?
Maybe I can ask something else. So is there anything special about zero scalar curvature?
Well, for this talk, of course, they don't really appear because we're deforming from constant positive scalar curvature because they're Fano Kähler Einstein. but yeah, well, in my opinion, yes, because well, we ended up we ended up in this place sort of uh deforming Fano Kähler Einstein, but you know, I one secret hope that I have for this line of research is, the notice also, right, that the stability condition that I wrote down exists on a Kähler manifold. In a way, it's not really like engaging with the generalized Kähler geometry. I mean, it is because it involves the Poisson tensor, but it's kind of a trick. It's like it's it's just because we're deforming away from Kähler. Like more generally, I would like to take, yeah, even for instance, these kind of these generalized Kähler-Ricci solitons that we know we have on the kind of non-diagonal Hopf surfaces. Like in a way, their existence should kind of be predicted by a kind of notion of stability. And that's like the case of like zero scalar curvature. These all have like zero scalar curvature. And like that notion of stability should be predicted, or rather the existence of those metrics should be predicted by some kind of like more general notion of stability for the generalized Kähler classes that they lie in. Um, but
Okay, thank you.
yeah, but yeah, we don't have anything to say about that. And then yeah, I see in the chat, uh no, yeah, right. So that kind of relates. I guess what I was saying kind of relates to that. Like the most meaningful. So he asks, yeah, is the generalized version of the Kähler-Einstein problem understood already? Definitely not. What I can say, well, what I can say is the kind of natural notion of Einstein metric for generalized Kähler, if the Einstein constant is not zero, sort of immediately reduces in the compact setting to just being classically Kähler-Einstein. So the most interesting case is this case, is this kind of like Calabi-Yau type case. And here there are by now like lots of non-trivial examples of these things. But yeah, but I would say, whereas, Yau's theorem is quite old now, and it's sort of this pure PDE proof that doesn't really involve any of these kind of deeper algebraic structures like associated with, the Calabi program. Almost surely the correct sort of Calabi-Yau theorem in generalized Kähler geometry to sort of characterize the existence of these will involve all of this algebraic structure. It should involve a notion of stability. That seems to be the way it's looking now. But the short answer is actually, yeah, if anything, to me, it's sort of more interesting, but maybe even harder than at least doing this deformation stuff that we did here. Is the Calabi-Yau case related to the Donaldson symplectic Monge-Ampère conjecture? Maybe I don't know quite exactly which conjecture you mean. If you mean the kind of like symplectic triviality, like that every symplectic form on, for instance, T4 is like equivalent to a standard one. If that's what you mean, yes, I think, well, not maybe completely directly related to these questions, but I always kind of secretly thought that there was a way to answer those questions, maybe using generalized Kähler geometry and using like generalized Kähler-Ricci flow, but it's not completely direct. Like it might be possible, for instance, on T4 to take to take a symplectic form and then take sort of two complementary forms in the correct cohomology classes. So you have to kind of pick the cohomology classes correctly and then sort of show that those three forms can be deformed to define a generalized Kähler structure. And if you could do that, then we know that that generalized Kähler structure can be deformed to be the flat metric. And then so you would sort of canonically deform your given symplectic form to a standard one. Okay. Oh, you mean, yeah, okay. You mean this. Yeah. And then, right. I guess, right. Okay. So this conjecture that you say in the chat, I think that conjecture, possibly answers this question I was saying before. I think if you knew that conjecture, you could do what I just said, which is basically take a symplectic form on, for instance, on T4 and sort of show that it's part of a generalized Kähler structure. And then you could do what I said. And then sort of, and then answer this like symplectic triviality question. But yeah, so anyways, the short answer is sort of on the face of it, not exactly directly related, but I think there could be some interesting connection there.
Okay. Any more questions?
Yeah, I have a question. So, Goto did define notion of stability to study this uh, Hitchin-Kobayashi correspondence. So, would that
Mhm.
be any? Does it have any relation with this stability notion?
Well, I think, well, I guess as far as I'm aware, like kind of in the classic, I mean, at least as far as I'm aware, like historically, the kind of stability as it comes out of the like Donaldson-Uhlenbeck-Yau theorem, and yeah, like Kobayashi-Hitchin correspondence was kind of inspirational for like the story of K stability, but I don't think really like literally related in a rigorous way. I didn't really think. Sort of because the PDE is, well, I don't know, like the Hermitian Yang-Mills is semi-linear, whereas like these equations for constant scalar curvature, etc., are, well, they're much worse. They're quasi-linear. So I always thought that it was kind of inspirational for those notions of stability, but not literally related. So I think that my point being that I think the same is true here. I think that in a way that they're sort of maybe some kind of loosely related, but not literally, I don't think.
Okay, thank you.
Okay. Any other questions?
Yes, one more question. Is there anything special when the class of F is integral?
Yeah, I mean, well, in fact, we have to use that actually. Uh, so, yeah, well, of course, yeah. Then I mean, the point is you kind of have this quantization story once you have that, and yeah, there. Sorry, I need a second. Yeah. Anyways, maybe. Yeah, the short answer is yeah. I mean, I think that there are tools in the study of like geodesics in the Kähler world that sort of only hold in the like sort of using the quantization, using the fact that the class is integral, in making the connection to algebraic notions. Yeah. So no, yeah, it definitely matters.
Okay.
Yeah.
Okay. Are there any other questions? Okay. If not, then let's thank Jeffrey again, and thank you
Thank you.
everyone for coming. We'll see you next year.